And last time we worked on an example, I'll pull it up here, which looked like, I'm going to go, it's in here somewhere. That's on page 3. Okay, so we were looking at this example. We had x prime was equal to 0 minus 2, 2, 4 times x. And we did a bunch of algebra on this thing. And when we were finished, what we arrived at was the conclusion that our solution, x, looked like c1 e to the 2t v1, I should be a little bit careful here, 1 minus 1, plus c2 e to the 2t times this mysterious vector 0 minus 1 half, plus t times the vector 1 minus 1. And what we're going to do today is going to be based on, so to do this we did a bunch of algebra, right? Like grindy, like different derivatives and substitutions into an equation, and then manipulating a bunch of crap with second order, like constant coefficient linear differential equations. What we'd like to do instead is, it would be nice if we could somehow extract what these vectors are directly from the matrix in the same way that we do in the diagonalizable case. So what we're going to do is we're going to guess that if A is diagonalizable, and we're going to start with a 2 by 2 case, that if A is, defective, then I can find a first solution by writing down e to the lambda t v, where v is an eigenvector for A. And the structure of the second solution, following our guess here, that's an eigenvector of A, and this is some mystery vector. So if you write down x2, it's e to the lambda t times v2 plus t times v1. So we're going to guess that this is a general thing that holds here. That I can, if I have a differential equation with a defective matrix, that is a solution. I'm almost like thinking of this as a trial solution. I'm guessing that this is the form of a second solution to a differential equation.
Is v2 an eigenvector?
V2 is not, v1 will turn out to be an eigenvector, but not v2.
V2 is something mysterious.
Yeah, that's the, so in fact, this will turn out to be, this v2 right here, that when we produce this thing, this is going to turn out to be something called a generalized eigenvector. And it's related to the study, last time I sort of very briefly mentioned Jordan canonical form. That's what the v2 is, yep.
Are both eigenvalues the same?
This in a 2 by 2 matrix, to be defective, it has to have a single eigenvalue with a multiplicity 2. So in this case, these are the same. That's actually the problem, is that these are the same eigenvalue, but there's only one eigenvector. Yep.
And to be defective, does it need to have a 0 in it somewhere? Like,
No.
It doesn't?
Nope.
Okay.
That is absolutely not the case. In fact, I've got another example that we'll do by hand later that does not have a 0 inside of it. In fact, there's no way to look at a matrix and know that it's defective, which is really annoying. I can tell you if it's invertible because I can calculate the determinant, if it's square. I have no way to know it's defective unless I look at its eigenvalues and eigenvectors, which is a massive problem in application. Okay, so what we're going to do is we're going to guess the trial solution. X is equal to e to the lambda t v2 plus t v1 to the equation x prime is equal to ax. And I could work through the algebra of what happens next. So what we mean by this is, I'll even put the 2 here. What I mean by this is, if I took the derivative of that equation, and then I put that expression into both sides of the differential equation, and I multiplied everything out, so I did a whole lot of algebra, and I compare some like terms, and when the dust settles, I just made the decision that like showing you all this algebra wasn't like, useful. It's not a good use of your time. It's written in my notes and it's in the book. You plug this trial solution into this differential equation, and what you discover is this will solve this differential equation. Something of this form will solve this differential equation if. So x2 is equal to e to the lambda t v2 plus t v1 solves the differential equation if two conditions are met. One, a times v1 is equal to lambda times v1, which says v1 should be an eigenvector. And two, a v2 is equal to lambda v2 plus v1. So that's great. We've managed to reduce the problem of finding a solution to the problem of solving this system of vector equations. But those vector equations are kind of obnoxious to work with. So we're going to take these vector equations and we're going to rewrite them in a way that's going to give us an algorithm we can use to figure out what the v2 and the v1 have to be. So if I rewrite these slightly, I can rewrite this equation as, just imagine, this is equivalent to finding the eigenvector equation, but v2 depends on the choice of v1, and then I'm going to have this obnoxious thing where I'm trying to solve for v2 in a matrix equation, which is some mad row reduction. I don't really want to row reduce if I can get away with it. So I'm going to rewrite this equation as a minus lambda I v1 is equal to 0. And this second equation can be rewritten to be a minus lambda I v2 is equal to v1. So you just do some algebra and you get this set of equations. This is almost what we want. I can almost use this as an algorithm. But again, I don't want to solve an equation by row reducing. That sucks. Instead, what I'm going to do is I'm going to go one step further, and I'm going to rewrite this set of equations as, well, if I took the second equation and I multiplied both sides by a minus lambda I, so if I took the equation a minus lambda I v2 is equal to v1, which is an equation I'd like to solve, and I multiply on the left by a minus lambda I, a minus lambda I v1, what is a minus lambda I v1 equal to?
0.
0 by the first equation, right? So I want that equation and this equation to be true at the same time. I ultimately come down to, I can find the vectors v1 and v2. So v1 and v2 satisfy the following. A minus lambda I squared v2 is equal to 0. And a minus lambda I v2 is equal to v1. And necessarily, because I want that to be an eigenvector for the original matrix, it must be the case that v1 is not the 0 vector. So there's an intermediate condition here, which is to say, it better be the case that whatever we choose for our v2, you shouldn't get 0 out by multiplying it in. If you accidentally picked an eigenvector, you break the whole thing. So
When you square it, you want it to be 0.
no. I want to pick a v2 that I want that to be true. I want to pick a v2 so that if I take a minus lambda I squared times v2, I get 0. But if I do a minus lambda a to the first, I don't get 0. Because whatever that vector is, I want to call that v1. So now I'm going to give an algorithm, and then I'm just going to do a whole bunch of examples of using the algorithm, because this looks like abstract nonsense until I show you a concrete algorithm for doing it, I think. So, step 1, if given a problem, x prime is equal to ax. Step 1 is to compute the eigenvalues and eigenvectors of A. If you're diagonalizable, you just get off the road right there and write down the solution. If you're not, you're going to calculate a minus lambda I and A minus lambda I squared. Because I need A minus lambda I and A minus lambda I to do the next part of the equation. Step 3, pick a solution to A minus lambda I squared V2 is equal to 0. You just pick V2, it makes that true. As long as, so here you also need A minus lambda I V2 to not be equal to 0. Step 4, you're going to set V1 to be equal to A minus lambda I V2 because that was needed, that's a necessary condition for our system of equations, is that A minus lambda I V1 is equal to 0. And then once you have that information, you can just write the solution down. Step 5 is going to be, step 5, you're going to write x2 as e to the lambda t times v2 plus t v1. That'll be your second solution. So let's apply that algorithm, this sort of 5-step algorithm. We're going to apply that to the problem that I wrote down last time and see if it's any easier than doing a bunch of vector mathematics. So we started with, here's an example, x prime is equal to 0 minus 2, 2, 4 times x. And I want to find the general solution to that vector differential equation. Step 1 says that we're supposed to figure out the eigenvalues and eigenvectors. So 1, lambda is equal to 2, and the eigenspace is the span of 1 minus 1. Automatically, I know that right now the matrix is defective. I can't go any further to a general solution because I don't have enough eigenvectors. What I can do from this information is I can write down my first solution, e to the 2t times 1 minus 1. That information gives me one solution to the differential equation. But I need 2 linearly independent solutions to a 2x2 system. So step 2, I'm going to write down a minus 2i, which is minus 2, minus 2, 2, 2. And I'm going to write down a minus 2i squared. And if you do that calculation, you'll find that you get the 0 matrix out. Now this is a feature that real numbers don't have, right? You don't square a real number and get 0. The only thing that does that is 0, right? So there's something weird about the fact that this is even possible. I've got a non-zero thing that I squared and I got 0 out the other side. These are called nilpotent matrices. They're studied all the time because of the way they show up in what we're doing right now. So a nilpotent matrix is one that has the property that a to the n is equal to 0 for some n. All right, so now I'm going to do step 3, which says I'm supposed to pick a solution to a minus lambda I squared v2 is equal to 0. Well, that's pretty easy to do. So what I'm being asked to do for step 3 is I want to solve a minus 2i squared v2 is equal to 0. But that's 0, 0, 0, 0 times v2 is equal to 0. I got a lot of choices for solutions to that equation. I can choose anything I want, as long as when I pick v2, I can then do the next step to make a non-zero v1. So a typical move here, and I'm going to do 2 different examples to show you what happens. One thing you might do is you might guess, or you might choose rather, v2 is equal to 1, 0. I have free choices. As long as I don't pick an eigenvector when I make that choice, anything works. So I could pick any v2 I want, as long as I didn't pick an eigenvector. Did I pick an eigenvector? How do you know?
There's only one
There's only one eigenvector, but how do I know that I didn't accidentally pick it's not a multiple of this, right? It can't be in the span of that eigenvector. I can't choose any multiple of 1, -1 here. So I'm going to pick a really easy vector, like 1, 0. Then the next step says, now we're going to find v1 by doing a minus lambda I times v2. So we're going to set v1 to be equal to -2, -2, 2, 2 times v2, which was 1, 0. And that gets us the vector -2, 2. And we can stop for a second and ask ourselves, the algorithm says that this is supposed to be an eigenvector of the matrix. Is it?
Yes.
Well, it's a scalar multiple of this, and so it must be, so we're okay. We want that. We want to verify that the thing we chose here for v1 is an eigenvector. And then step 5 is you just write the solution down. Write the solution as x2 is equal to e to the 2t times v2, which was 1, 0, plus t times v1, which was -2, 2. It might seem weird that I could pick any vector I wanted right here, but remember, that's adjusted for the fact that the v1 had to vary with it. v2 and v1 here come as a pair. And so when you're finished, you solve the equation. The general solution is, the general solution x is the bit that you constructed from the original eigenvalue, an eigenvector, plus this bit that you've thrown together by doing this generalized eigenvector nonsense. And that's a version of the general solution to the differential equation. So you can imagine, you can see that you have to be a little bit careful here. I can't just choose any eigenvector, because if I factored a 2 out of this and tried to throw it inside the coefficient, I would also have to divide this one by 2. They're stuck together in some way. Yep.
Why don't you have to use the same v1 in here?
Because this, if I factor a number, if I scale this, that gets absorbed into this arbitrary constant.
Okay.
If I try to scale this vector by pulling it into the constant, this has to adjust at the same time. So these vectors are bound together.
Okay.
It's almost like you're trying to find two different lines that dictate the solution, and that's the way that we're doing it, right? So these are fused together in a way that that one's not.
Okay.
I'm a little confused on how you knew a minus 2i squared is the zero matrix.
Oh, I just did the multiplication.
Okay.
So if you actually write down -2, -2, 2, 2 times -2, -2, 2, 2, and then you say this times this is 0, and this times this is, did I get this wrong?
No, it's
Zero.
It's
Yeah, 0, and this times this is 0, and this times it's just by multiplication it turns out to be the zero matrix. Yep.
Yesterday we wrote a solution that was the
Different.
V2. Yeah.
So the solution that we wrote yesterday, we did directly from the algebra, right? But if you look at the solution we wrote yesterday, because we chose because this vector we made a free choice of, if we had chosen at this position the same vector that showed up yesterday, the 0, -1/2, that vector would have adjusted appropriately.
If you factor out -2, we get the same answer as yesterday, right?
Well, no, but this vector yesterday was 0 -1/2, which is another legal choice for my second vector. So, it's weird, right? There's more going on here than just yep.
Will a minus like lambda I squared, will that always be the zero?
So, in fact, yes. So that's something where the matrices that we end up producing here, if I know that this chain, essentially this is an argument called a chain. If I take this thing and produce an a minus lambda I squared v, which spits out a 0, then this will be 0, this will be v1, which isn't 0, and then there'll be some vector at the bottom of the chain as well. So because there's going to be an eigenvector and a generalized eigenvector, that if there was a cube here, I could keep the process going and make more generalized eigenvectors, but there can't be more. So it's going to be a feature when we're studying these things that when we start taking powers of this matrix, at the end of the chain is always going to be the zero matrix. It basically tells you where to start. Yep.
Is there a best or an optimal vector to choose for V2?
So that depends on applications, probably. Like if you're trying to think about I would say generally the easiest vector to compute with is the right choice for V2, and 1, 0 is a pretty good one. Yep.
So what you were saying was when you scale this up, like if you had a 3 by 3.
Oh, we're gonna do a 3 by 3.
Oh, we are. So
Yeah.
that one you're gonna have to cube it, or do you just?
There'll be well, it depends. There's two different. I want to show you two different cases. This gets hairy fast, is the point. Okay. So let's do the same process again, but let's do it with a 3 by 3 matrix. So you've anticipated where this was going. So the 2 by 2 case always works exactly the same way. Every one of the 2 by 2s looks like that. In fact, maybe I can do one more 2 by 2 because I have it written out. This will be pretty quick. So we'll do another 2 by 2 example, and then we'll shift to the 3 by 3s. So if I wrote down x prime is equal to 1, 1 minus 1, 3x, and in step 1, I tell you that this matrix A, which is 1, 1 minus 1, 3, has characteristic polynomial equal to lambda minus 2 squared. And it has an eigenvector, v, which is 1, 1. Just one eigenvector. So this is another defective matrix. If I'm trying to solve the equation, what step 2 says I'm supposed to do is write down a minus 2I, which I guess is minus 1, 1, minus 1, 1. And then it shouldn't be surprising that a minus 2I squared, if you actually calculate that out, you end up with 0, 0, 0, 0 again. In step 3, we are supposed to choose a solution to 0, 0, 0, 0, v2 is equal to 0. That is a minus 2I squared v2 is equal to 0. Now we don't have to pick 1, 0. Pick anything you want.
0, 1.
0. Okay, that's a good one. So let's pick v2 is equal to 0, 1 this time. Now, 0, 1 is not a scalar multiple of 1, 1, so we've picked something that will not be an eigenvector. So step 4, we're going to set v1 equal to a minus 2I v2, which is minus 1, 1, minus 1, 1 times 0, 1. And that gets us the vector 1, 1. Oh, look, that's what it's an eigenvector. It's exactly, you managed to hit it on the dot this time. There you go. Okay, so now we know v2 is equal to 0, 1, and v1 is equal to 1, 1. And so we can construct our second solution, x2, as being equal to e to the 2t times v2 plus t v1, which is e to the 2t times 0, 1 plus t times 1, 1. It's basically the same every time. Yep.
Is it guaranteed if we don't pick a eigenvector for v2 that
v1 will be non-zero. Yeah. So if you do this step and you calculate v1 and you get the 0 vector out the other side, it means you accidentally picked an eigenvector back on this step and you got to pick something else. So I have to be able to, when I construct v1, if you had accidentally picked an eigenvector, that would have turned into nothing.
And we can also verify that minus lambda I times v2 will not be equal to 0.
Yeah. So you, at the same time, basically. So I've simultaneously verified that it's not 0, and also I set it equal to v1. All right, so now let's get to Azalea's question. We'll do some matrix calculations. Yeah. I've been waiting for this. Oh no, I can't find my calculations. I can't do it. Just kidding.
Oh no.
Okay, so before we do this, I want to point out that you should think already that this seems kind of fussy, right? Like, this is just the 2 by 2 case. Like, I have this kind of repeated structure, and I have to like have this modification of my original solution that has this line stuck inside here. So let's look at example 3. And then example 4 will be the full glory of the 3x3 case. All right, so this example looks like the following. So we're going to solve x prime is equal to 5, 2, negative 1, 1, 6, minus 1, 3, 6, 1 times x. Now, again, one of the points of this is you cannot tell what's going on just by looking at the matrix. You have to look at the eigenstructure. Step 1, the characteristic polynomial of this is minus lambda minus 4 to the third. Okay, so lambda is equal to 4 with algebraic multiplicity 3. 3 different things could happen here. There could be 3 distinct eigenvectors, there could be 2 eigenvectors, or there could just be 1. This could be a 1, 2, or 3-dimensional eigenspace. Yep.
Does this only work if it's the same eigenvalue? Or can it be like 1 squared and then another eigenvalue?
Oh, we're gonna like yeah. So if one of them is distinct and another one is repeated, you could still have that same. There's not enough eigenvector problems. It's gonna look exactly like what's gonna happen here.
Oh.
Okay. So the eigenspace this time. Here's what the eigenvectors look like. Eigenvectors are the span of minus 2, 1, 0 and 1, 0, 1. So this matrix is defective, but it's only defective by one eigenvector, right? So there's supposed to be 3 eigenvectors, but there's only 2 of them. So before I go any further in the problem, from this point, I could write down my first part of my general solution looks like e to the 4t times minus 2, 1, 0. And my second part of the general solution looks like e to the 4t times 1, 0, 1. And my third part is, oh, I've got to do that again. So I have one missing solution here. The algebraic multiplicity of this was 3. I only have 2 eigenvectors, which means I'm going to have to use one generalized eigenvalue. So this solution is going to look like e to the 4t times v2 plus t times v1. Exactly the same as the 2x2 case. I was missing a solution, so I make one by doing the generalized eigenvalue trick, or eigenvector trick. And at that point, you just do the same thing as before. This isn't all that exciting, but I'll work through the math anyway because we've already done it. Step 2 was supposed to be, we write down a minus 4i, which is 1, 2, negative 1, 1, 2, negative 1, 3, 6, negative 3. And then, if all is right in the world, when I square this thing, I should get the 0 matrix, and indeed I do. I only need one generalized eigenvector, so I should hope that that thing disappeared where I got that free choice. If you want to verify the matrix math, you can. That this times this is equal to the 0 matrix. Or you can just believe me. Step 3. We're going to pick a solution to 0, 0, 0, 0, 0, 0, 0, 0, 0, v2 is equal to 0. I'm going to pick an easy one this time. I pick v2 is equal to 1, 0, 0. I'm just going to try that. I'm not even going to bother to see if this is in the span of these. I'm just going to pick that vector and hope that I avoided the eigenspace. Because remember, it's not just these 2 vectors, it's anything in the span of those 2 vectors is also an eigenvector. So how am I going to check to see? I'm just going to declare v1 to be equal to a minus 4i v2, which is 1, 2, negative 1, 1, 2, negative 1, 3, 6, negative 3, times 1, 0, 0, and that's the vector 1, 1, 3. Cool. It's not 0. I have effectively decided my v1. If that had been equal to 0, it means I accidentally picked an eigenvector back at this step, and I got to pick a new choice. Well, that's all the information I need to fill out my second solution. Yep.
Wait, it's still doable with like one, like missing two of them?
Yes.
Okay.
That's the last thing I'm going to do is if you're missing two vectors. The form of the solution is different in that case. And so the last thing we're going to do today is I'm going to show you what happens if there's multiplicity 3 but only one eigenvector. So I guess the last step moves there.
So is that in the span of the? So that one.
It's
has
not.
To be,
This one is an eigenvector. You can actually verify that it's in the span of these.
Yeah.
I think it's 3 times this vector plus this one.
yeah.
Right? So it's
Okay.
definitely in the span of these. There's more delicacy here. This vector depended on this choice, and it's in the plane of these two vectors, but it doesn't have to be these two vectors, right? The reason that you want to know these a lot of times is because these give you the not weird solutions. You can just write those down immediately, right? Otherwise, when you did this step, you'd have to say, hey, look, I found an eigenvector, which lets me write down this solution. How am I going to find the other one? Look at the eigenspace and avoid that vector. That sucks. So, all right. So step 5 here would be just to write down that your x3, like every other time, is going to be of the form e to the 4t times 113 plus t times 100. And then your general solution will be c1 x1 plus c2 x2 plus c3 x3.
Wait, was it V2 100?
Did I screw something up?
Was it?
Yeah, it should be 100 plus.
Oh, I got that backwards. Yeah, sorry. 100 plus t times 113. There we go. Yeah, v2 plus t v1. And then your general solution x is x1, c1 x1 plus c2 x2 plus c3 x3. So you've written down x1, x2, and x3. So you can just write the general solution of that combination. If you did that on exam, I'd be happy with it. If you wrote down x1 is this, x2 is this, x3 is that, and the general solution is the combination, that's fine. You don't have to repeat yourself. Okay, now, for the most interesting case, it's like at least 3 of you have suggested this is coming now. What happens if I only have one eigenvector in a case where there's lots of this happening? This is the last example that we'll do today. Which even says, where's my sheet that says last example on it? Last case, there we go. All right, so this is, I think, example 5 for the day here. So we're going to look at A is equal to 1, 2, 0, 1, 1, 2, 0, minus 1, 1. And we'll look at x prime is equal to ax. And for step 1 in this case, the characteristic polynomial is equal to negative lambda minus 1 to the 3rd. So lambda is equal to 1 with algebraic multiplicity 3. And this time, there's only one eigenvector. V is just equal to the span of minus 2, 0, 1. So I can write down one solution. x1 is equal to e to the t times minus 2, 0, 1. And now I need an x2 and an x3. I'm missing 2 vectors. The geometric multiplicity is 2 less than it should be instead of 1. So the way that we write this is going to have the form e to the t times v2 plus t v1. And this is going to have the form, and here I want to think where this might have come from, e to the t times v3 plus t v2 plus 1 over 2 factorial t squared v1.
Take the unit though?
It's kind of like a power series.
It does look like a power series, doesn't it? Which power series does it kind of look like? Kind of like e to the x, right? So it turns out that the actual correct way of doing this, which we can't do in here, is there's this thing called the matrix exponential that you can define.
You can't do it in here. Like, you can't.
I don't have time to do it. So it's in the book.
Not allowed.
Like, we don't have time to solve this problem, or you.
No, I'm going to solve the problem. I can't tell you why this is the form of the solution.
Oh.
I would like to. I want to justify why it is this. the answer is that you form something called the matrix exponential, so e to the at. So it's an exponential, but you put a matrix up there, and it turns out to be equal to a sum, n goes from 0 to infinity, of a to the n over n factorial. There's a power series of matrices. And then, if a matrix vanishes at some point, like if it's nilpotent, that will stop. It won't be infinite, right? Like if a cubed was equal to 0, it's just done. So this is lurking in the background of all this. And I cannot, there's an entire chapter of the book dedicated to the matrix exponential. It's a beautiful idea. You'll see it in later classes, probably.
Well, 344.
No. I mean, actually, maybe. I really like the matrix exponential, but that's why it looks like the exponential function. Yeah.
So if it's missing 2, does that mean like a minus lambda I cubed is
Yes.
going to be 0, and then
Yep.
a minus lambda I squared is going to be something else?
Yep. So in this case, because we have 2 missing pieces of information, we're going to write down a minus I squared, and a minus I to the third, and this is where the 0 matrix is going to show up.
Minus I, because.
Well, yeah, minus, I should put a 1 here. Yeah, 1, 1, 1. So I basically do the chain until I hit the zeros, and then once I hit the zeros, I know what to do. I'm going to solve a minus I to the third v3 is equal to 0, and once I have v3, I can set v2 to be equal to a minus I times v3. And once I have v2, I can set v1 to be equal to a minus I v1, or v2. So I can work my way backwards.
Does that mean a minus 1 squared?
That's the square here.
Okay.
Yep. No. It's once I have v3, is that right? A minus I want my eigenvector to be, it's like this. It's like this. The idea is the following. So if I know that a minus I cubed v3 is equal to 0, then that means I know that a minus I times a minus I squared v3 is equal to 0. So that means that's an eigenvector right there. Right? So I'm going to call that v1. Right? And then the intermediate vector, so v1 is going to be a minus I squared v3, and v2 will just be a minus I v3. The sort of intermediate
For both
vector.
of them, or just for the x?
For both. You find these and you put them into everything.
Oh, they work for both.
They work for both. Yeah, there's not like 2 sets of equations to solve here. It's like you solve the matrix exponential, whatever the terms have to be, and then you just pull off the terms and stick them where they're supposed to go. It's almost like this is the derivative of this in some way. Right? If you took the derivative of this expression, you got that one. Forget the e to the t's for a second. This polynomial has a derivative that is this polynomial. You're skeptical. But it's true.
No, I really do.
Oh, I was looking at Bowie.
Oh.
It's true though. The derivative of t squared over 2 is t. I know there's vectors in there. Just don't pay attention to vectors. Anyway, so that's how the process goes. You build the v1 and the v2 from the v3 by doing exactly the same process. You need the v1 to be an eigenvector. How do you get it? You write it down like this. And then this intermediate power is where the v2 comes from. So, yeah. It's a lot. So what do you do with it? Well, I guess we should actually solve this damn thing. Okay, so I guess step 2 is we need to calculate a minus I squared, and a minus I to the third. Well, I didn't do this by hand. I took this off an example in the book to make sure I picked something that was reasonable. Sorry. That is this one. Okay, yep. All right, so this has the following. A minus I is equal to 0, 2, 0, 1, 0, 2, 0, minus 1, 0. And a minus I squared is equal to 2, 0, 4, 0, 0, 0, minus 1, 0, 2. And perhaps unsurprisingly, A minus I to the third is a matrix of zeros. Then we're going to pick, so it's step 3. We're going to pick a vector v3 that solves 0, 0, 0, 0, 0, 0, 0, 0, 0, v3 is equal to 0. I can think of an easy one.
1, 0, 0.
Shot, that's a pretty good choice. v3 is equal to 1, 0, 0. If I multiply v3 by a minus I, that gives me v2. And that was, the hell was it? 0, 2, 0, 1, 0, 2. Then you think the powers that be, the computers were invented at some point in the past. And that gets you the vector 0, 1, 0. There's your v2. And then finally, v1 is equal to a minus I times v2, which is 0, 2, 0, 1, 0, 2, 0, minus 1, 0 times 0, 1, 0, which is 2, 0, negative 1. And it's negative 1 times the eigenvector that we found, right? In the beginning. So it is an eigenvector. So then we just write the solution down. We have v3, v2, and v1. We have the original structure of the matrix. And so our final solution here is x is equal to c1 e to the t times the original vector we found, which I think was minus 2, 0, 1. That was from the eigenvalue and eigenvector at the beginning. c2 times e to the t times v2 plus tv1. So v2 plus tv1 plus c3 e to the t times v3, which was 1, 0, 0, plus tv2, which was 0, 1, 0, plus 1/2 of t squared times t1, 2, 0, negative 1. And then you sit back and you think, if this is the easiest possible case of these problems, differential equations must be hard. There's nothing easier than linear first order equations with a matrix of constant coefficients inside of it. So if I change a single thing about the setup to what we've done here, it all breaks. So what I did not tell you earlier, when we were talking about predator-prey models, is that if you go on Wikipedia and you look up a predator-prey model, the most common model that's used in biological engineering, environmental sciences, it looks like this. X prime, Y prime, so I'll even write like that, yeah, X prime, Y prime is equal to AX plus BXY, and Y prime is CXY plus DY. That's a non-linear system. I can't even factor that as a matrix because I can't write this as a matrix times anything. There's no vector times a matrix here. This is nonlinear. And now the question becomes, how on earth are we going to study nonlinear systems? For you guys, what I'm going to do is I'm going to draw you a bunch of pretty pictures and we're going to sort of interpret what we think is happening from the phase plots. This is not something that you're responsible for on an exam, right? But I want you to show you almost every actual differential equation system is nonlinear. So you can study it with a computer by producing pictures of what's going on. However, if you remember when we studied remember that thing we wrote down with the Hessian matrix way back in 241 where we had like the Taylor polynomial, but there were matrices inside of it? Oh yeah. It's what you do is you take the derivative of this problem and it turns it into a matrix problem. Because the secret of calculus is that everything is aligned. So you do a linear approximation of this nonlinear system, and then once it's a linear approximation, you can do linear algebra to it. So the rest of your natural life as a scientist is basically going to be You're studying some problem. It has some kind of gnarly nonlinear system that describes it. So you replace the nonlinear system with a linear one by taking a derivative, and then you do linear algebra to it, and you will never escape. Calculus and linear algebra will be the rest of your existence, unless you're a computer scientist of some kind, and then there's no calculus. It's just linear algebra. All right. So on Thursday, what I'll talk about is the phase portraits, and then on Friday we will do sort of bringing it all together. I will post sort of exam preparatory material sometime tomorrow. So I'll see you guys later.